Hello everyone, my name is Neha and this is the third lecture on electronic circuits. In this lecture, we are going to learn about JFET amplifiers. JFET amplifiers, they are commonly used to amplify the AC signals. And if we compare the JFET amplifiers with the bipolar junction transistor amplifiers, then we'll get to know that the input impedance in JFET amplifiers is very high compared to your BJT amplifiers. And the voltage gain in JFET amplifiers is low compared to BJT. So that's the disadvantage in JFET amplifiers, that it has low voltage gain. JFET amplifiers, it is basically divided into three types of amplifiers. First is the common source amplifier, second is the common gate amplifier, and the third one is the common drain amplifier. I hope you remember in the bipolar junction transistor, you might have done small signal amplifier operation. You might have seen AC equivalent circuit of different types of amplifiers like your common emitter amplifier, common collector amplifier, common base amplifier, emitter followers, etc. So the circuit and the AC model, how you construct, are going to be pretty much similar in this one as well. The only difference is that you're using JFET device. So you'll be replacing the BJT with the JFET device, and you're going to analyze how the circuit performs for different configurations. Now, so before we learn about these three different types of configuration, I would like to talk about transconductance, which is GM. So this transconductance curve we have already seen in the previous lecture, and so I'm going to explain it again, and we're going to see what formulas can we apply to calculate the transconductance. So this curve you see here is drawn between ID and VGS, where ID stands for your drain current and VGS is the voltage between the gate and the source. And on the left hand side, you see this formula which represents your transconductance, and transconductance is basically rate of change of drain current divided by rate of change of VGS, which is your gate to source voltage. And this formula has been derived from this curve, and you will be using this formula when you analyze the different JFET amplifier configurations. So let's move on to the next slide. So this is the first type of JFET amplifier, which is the common source amplifier. And as its name says, common source. So the source of the JFET is going to be common to the with respect to the two other these terminals, the gate and the drain. And in this, the input in this type of configuration, the input is applied from the gate side and the output is taken from the drain side, and this source is going to be your common. So this type of amplifier, common source amplifier, it has high input impedance and it has moderate voltage gain, and also the input and output voltage, they are 180 degree out of phase. As you can see here, this is our input signal, and you can see our output signal is out of phase by 180 degree. And so this is the initial circuit where you see the AC signal is going in here, and then you have all these three resistances. RG is for the gate resistance, and this gate resistance is very high. And then you have RD, which is the drain resistance, and this RS is the source resistance. And then you have this bypass capacitor, CS. And then you have coupling capacitor, C out of 100 microfarad, and then the Cn is again the coupling capacitor of 0.1 microfarad, and then you have a load resistance of 10 kilo ohm. The resistance between the gate and the source is going to be very high in this case, and that's what we I said it before, that it has the high input impedance. So this is a common source amplifier, and we are going to see the AC equivalent model for this particular circuit. So this circuit basically shows the AC equivalent circuit of the previous circuit which you saw. So this has been formed from this circuit. Okay, so this RG is your 1 mega ohm resistance, and this represents your input voltage, and then this current source represents your drain current, and this drain current is equal to GM and then now you should know, like, what is this GM basically is your transconductance, and VGS is the voltage between gate and source. And then this RL, this is the new term here, a small RL, which is basically the parallel combination of the drain resistance and the load resistance. So let's go back to the previous circuit to see how we have got this parallel resistance. So you see here, the output is basically coming out from the drain side. So this resistance will be in parallel combination with this RD, and once you find the parallel combination, that will be your small RL. Okay, so on the input side, RG will be equals to your input impedance, and which is very high of 1 mega ohm. And this occurs because with practically zero gate current, the gate source resistance, designated RGS, approximately approaches to infinite. Now we're going to see some of the formulas if you do the derivation for this particular circuit to find out the voltage gain. Then these equations you'll be using, you know that voltage gain or any gain is basically equals to the output upon input, and here we are measuring the voltage gain, so the formula will be output voltage upon input voltage. So we have to see how to find the output voltage. In this case, the output basically is basically you will be taking out from this load resistance. So that means your V out should be ID into RL by using the Ohm's law formula. V out is going to be ID into RL, and that's what you see here. And then input should be your input voltage, which is your V in, and this V in is across this RG. So that's your voltage gain. ID is equals to GM, and then this ID. What is ID? It's already written here. ID is basically the multiplication of transconductance GM and VGS. So ID is GM VGS, and your input voltage V in is basically your VGS, which is gate to source voltage. Okay, so this is going back to this circuit. So here the voltage you're getting here is your input voltage, gate to source voltage, and that's what we have here, where Vn is equals to VGS. And if you put these value, the value of ID, the drain current, and the input voltage into this above equation, then you're going to get this, where AV is equals to GM VGS RL upon VGS. Now, if you so we have this this term VGS on numerator and the denominator, so it's going to cancel it out, and then the equation will be simplified to this AV is equals to GM RL. Now, if in this circuit, let's go back to this circuit. So if in this circuit, if you're not using the bypass capacitor, so this capacitor, if it is not connected, then your formula is going to be a little different. You'll be using this formula where your voltage gain will be equal to GM-RL upon 1 plus GM-RS. So this formula you'll be using when if your RS is not bypassed. Okay, so these equations you will be using to find out the voltage gain for common source JFET amplifiers. Now let's move on to the next type of amplifier, which is your common drain amplifier. And this type of amplifier is usually referred to as a source follower. I hope you remember in the BJT we had like emitter follower, and similar to that, this is a source follower amplifier. So So here in the source follower, a source follower has a high input impedance and low output impedance and a voltage gain of less than 1 or unity. So the voltage gain which you are going to obtain from this type of amplifier is always going to be less than 1. So in this type of amplifier, the signal is applied to the gain, whereas the output is taken out from the source. As you can see here, the signal is being applied to the gate, and the output is basically we are getting from the source side. And what is common to both the terminal is the drain. So that's why this is called your common drain amplifier. Now let's see different equations to find the voltage gain for this particular circuit, and on the right you see the AC equivalent circuit of common drain amplifier. Okay, so in this circuit, this is a little bit different than the circuit AC equivalent circuit which you saw for the common source. Now in this one, we have shown RGS, which represents very high resistance of the reverse bias gate source. And the equation for output voltage for this particular AC circuit will be V out. So output you are taking out from here, from this source side, and so which means the output should be so this current will be flowing out here. Okay, so ID RL. So the same formula which you have used in the previous AC circuit, you will be using ID RL is going to be your output voltage, where ID is your GM VGS, and that's what you see here, and RL. And your input voltage, now in this case the input voltage is going to be a little bit different because we have to consider the VGS across this and then this. So we are going to consider this branch and this branch as well. So if you apply the Kirchhoff voltage law, then you will get the V in input voltage. You will get the input voltage which will be equal to so this input voltage will be equal to your VGS, this voltage, and then GM VGS, which is VG, and then GM VGS RL. So this is your input voltage across this RG. This is the input voltage at this point is your V in, and that's what you see here, and this is your VGS. So let me maybe use a pen to show what loop you will be using. So this is going to be your loop. Okay, so what do you see here? So this is your V in, this is your V in input voltage, and then you have this VGS over here, and then you have VGS over here, and then you have this RL in which ID current is flowing. And so let's say as ID is flowing. So this is the loop you're going to take, and once you do that, you will get this equation Vn is equals to VGS plus GM VGS, which represents your ID, into RL. So I'm going to erase this one. Okay, so that's how you calculate the input voltage. And once you know the input voltage, then you can easily calculate the voltage gain, because voltage gain is basically equals to V out by V in. So V out is your GM VGS RL, and then this is your VGS plus GM VGS RL. You can take VGS here common. So once you take the VGS common, then you can cancel this VGS by this KGS. So you put this value over here, you put this whole value over here, and then take the VGS common at the bottom and then cancel it out with the numerator, and then you will get this equation which says AV is equals to GMRL upon 1 plus GMRL. So that's how you calculate the voltage gain. And if you have to calculate the output impedance, then the output impedance can be calculated by this formula. Z out is equals to RS parallel to the 1 by GM, where GM is your transconductance. So you will be using this formula to calculate the output impedance. There's one thing to note here is that source follower, the voltage gain which you are going to obtain here is always going to be less than 1. Now moving on to the next type of amplifier. So this is the third type, and this is the common gate amplifier, which has a moderate voltage gain. And in this type of gate amplifier, JFET amplifier, the input impedance is low, and that's the reason this type of JFET amplifiers is not seldom used. So let's see the circuit over here. We have common gate. You know that this is your JFET and this is the gate terminal, which is common to the source and the drain. So the input is going through the source side, and the output is basically you're taking through the drain side. So this RL is your load resistance, and you're taking out the output from the load side. And the CN and C out, they are your coupling capacitor. Now we're going to see the AC model for this particular circuit. So for this particular circuit, this is the AC model. This is the input voltage, and RS is the source resistance. 1 by GM represents the transconductance, and this current source represents your ID. So this symbol which you see here, basically it represents the current source, and current here is ID, which is equals to GM VGS, and RL will be equal to parallel combination of RD and capital RL, which is the load resistance. And here you get the output. Now let's see how we can calculate the voltage gain in this particular case. So output voltage is here, and output voltage we see here is basically the voltage across this branch RL, and that will be IDRL, and ID is GMVGS RL. So that's what we have here. And now the question is, what is the input voltage here? So input voltage is here, and you know that this is the node is going to be the same here as well. So this VN is going to be equal to your VGS. Okay, so you'll put these value into the formula, and you're going to get AV is equals to GMRL. Now in this case, if you have to calculate the input impedance, you will be using this formula. Zn is equals to RS parallel to 1 by GM. Okay, so this way you can calculate the input impedance. Now all the formulas you have seen for all three types of JFET amplifiers, you will be using those formulas into numerical problems, and you will be calculating voltage gain. So this was your common gate amplifier, and there's one thing I want to tell you in this lecture, that these model, you might be thinking how we have obtained these AC models from these circuits. So there's another topic on AC model, how you can convert it. That's another topic which is out of the scope of this course. But for now, just understand that this is the AC model representation of this. So this is the end of the lecture. Thank you so much for watching.